Today we're going to begin looking at parent functions. This is Chapter 1, Lesson 4. The objective that you are writing down for today will say, I will be able to classify types of functions based on their graphs and tables, and I will also be able to find the domain and range for different types of functions. Just like I mentioned before, domain and range is going to continue to show up in every section of this chapter. When you're ready, move on to the next slide. There are three types of parent functions that we are going to talk about today. When I'm talking about parent functions, that is the original graph before you translate it, slide it up or down or left or right. This is like the original starting function. The first one that you are probably the most familiar with is linear, and that is because the graph makes a straight line. The key point that you want to be aware of is if we have just a basic parent function that is linear, it is going to go through the point 0, 0. So let's take a moment. Here is our graph, and it goes through the point 0 on the x, 0 on the y. Let's look where the y-intercept, the B, is located. It cuts through the y-line. Here's our y-line going up and down. It's cutting through the y-line at 0 also. The next thing I'd like you to just look at is the slope. How much is this line rising compared to running? Well, in order to get from one point to the next, it looks like we rise 1, run 1, rise 1, run 1. So we are having a slope of rise 1, run 1, and that can be reduced to just the whole number 1. Let's look at our next graph, a quadratic function. The main point that I would like you to see right here is the vertex, the point where the graph stops going down and begins going up. That is called the vertex. The vertex goes through the point at 0, 0. This can change if we translate later this week. If we translate and move it, the main point may not, the vertex won't be at 0, 0. But for today, we're looking at just the parent function. Some other points the graph does go through are also here. That is the point 1, 1 and negative 1, 1. So just to see if we've got an idea of how to plot our points, make sure we're okay with writing our coordinates. This is a U-shaped graph, and it happens to open up. Anytime you see a graph that looks like a U shape, that is quadratic. The third type of graph that we're going to be working with throughout this year in Algebra 1-2 is exponential. This is the graph that can sometimes look like the letter J, and if it has been moved or translated, it could look like the letter L. We'll get to those later next semester. But a key point that I need you to see right here is this point at 0, 1. That is where the graph makes its sharp turn. Instead of going more flat, all of a sudden, it very quickly shoots up. If it's an exponential function, before we've translated it or moved it, that turning point is going to be at the point 0, 1. Now, the asymptote is a really important concept here. It occurs where y equals 0. So if you imagine this imaginary line right here, where y equals 0, we're cutting through the y line at 0. Notice my graph, as it comes down this way, it's approaching that y equals 0 line, but it will never ever touch. It'll keep getting closer and closer, but it will never cross down below. So that imaginary line that it's approaching but never touching is called the asymptote. Notice on the exponential graph that is increasing on the right side rapidly, and it's approaching 0 as it's going on the left. So as we move to the left, like we said, it's approaching the asymptote and approaching 0. As we move to the right, it is rapidly increasing. So these are the three different types of functions we're going to be looking at. Linear makes a straight line. Quadratic is the U-shaped parabola. Exponential increases rapidly and rather sharply, much more than the other two graphs. So once you take a moment, you have the three examples of the graphs drawn and some characteristics of each one written down. Go ahead and move on to the next slide. Let's take a moment and look at this first function. It says f of x equals 2x plus 3. I want to fill in this table of values and graph the function. Once I can see the function, it'll be very easy to decide, is it linear, quadratic, or exponential? Here's how we go about filling in this table. Just like we did in 1.2 evaluating. When x is negative 2, I want to see what my function is. So I'm going to come down here and say when I have a function and x is 2, anywhere on the other side of the equal sign where there's an x, I'm going to sub in that 2. Order of operations would tell me to multiply first. 2 times 2 is 4, plus 3 is 7. So when x is negative 2, the y would be 7. Did you catch my mistake? I put a positive 2 instead of a negative 2. That little tiny negative will totally change my answer. Negative 4 plus 3 is not 7. Negative 4 plus 3 is negative 1. I hope you caught my mistake before I did. So that is the point, negative 2, negative 1. So now I want to sub in my next x value where x is negative 1. So I'm going to have a function where x is negative 1. This is why we learned how to evaluate our functions in 1.3. I will take where the x is on the other side and I will sub in my negative 1. Order of operations does say multiply first, so 2 times negative 1 is negative 2, plus 3. Negative 2 plus 3 is 1. So when x is negative 1, the y value is a positive 1. So negative 1, positive 1. I'm wondering if you are catching on to my mistakes here today. I said the point was negative 2, negative 1. There we go. And then the next point is negative 1, positive 1. Here we go. Now let's sub in our 0. So I have a function when x is 0. So I'm going to sub in the 0 and then add 3. 2 times 0 is 0, plus 3 is 3. So when x is 0, the y value is 3. 1, 2, and 3. We have 2 more points to sub in, and then we'll be done. We will sub in f of 1, so we'll sub in 1 for the x. So 2 times 1 is 2, and then I'm going to add my 3, which would give me 5. And the last one that we do need to sub in is when f is 2. When the x is 2. So if I sub in a 2, since I ran out of space below, 2 times 2 is 4. 4 plus 3 is 7. So that would be the point 2, 7. Around 2 and then 1, 2, 3, 4, 5, 6, 7. And I forgot to graph my point 1, 5. There we go. You probably could have estimated where that point was based on the fact that it looks like it makes a perfect straight line. So go ahead and connect those points and make a straight line. So now we are able to tell that this function was in fact linear. So let's take a moment and look at our linear function and identify the domain and range. Remind yourself that domain is the x values, and we look at the x from left to right. Well, this line goes forever to the left, and it goes forever to the right. So our domain is simply negative infinity to positive infinity. Let's look at our range. That is the y line, the y values. Well, how low does the graph go? Well, it keeps going down, 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 down. So it goes forever in the negative direction. And how high does it go on the y-line? It continues on forever, infinitely, so positive infinity. So take a moment, make sure you have the table, the graph, and you've identified the domain and range, and that it is linear. One little note you might want to add to the bottom is if we have a function and it is just x to the first power, like we had y equals 2x plus 3, that is x to the first power. Just by looking at the equation, we could know that it was linear. Just a little note you might want to add. All right, here's our next one. We are going to go through the same process. We are going to start by subbing in a negative 2 for the x. This time we have f of negative 2 equal to, now put your x in parentheses, and you're going to sub in that negative 2. It does need to be in parentheses. That means we have two negative 2's. Well, negative 2 times negative 2 is a positive 4. So let's go ahead and find all of our points this time, and then we will graph them. If I sub in a negative 1, that would be negative 1 in parentheses squared. That means two negative 1's. A negative times a negative will be a positive 1. Now let's come in and sub in a 0. That will be 0 to the second power. So 2 zeros, 0 times 0 is 0. Now let's come over here and sub in, whoopsie, graph went away momentarily. Let's sub in a positive 1. And now we will simply just have 1 squared, which is 1 times 1, which is just 1. And our final one, let's go ahead and sub in a 2, which means we will have 2 squared. That is just 2 times 2, which is 4. I'm hoping you noticed a pattern here. Our answers went 4, 1, 0, and then 1, 4. The values repeated. There was a pattern that could be found. If we go ahead and graph these points now, we will see our graph. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Did you see that it did in fact make a U-shaped parabola? Do you remember what type of function this now is? The fact that it is a U-shaped parabola means it is a quadratic formula. Let's take a moment and look at the domain and range. Remember, domain is the x going from left to right. Does this graph have anywhere it begins on the left? It continues going left forever, so it does not have a beginning. So it goes forever into the negative direction. As far as how far right is it going, it never stops going right, so it continues to infinity. Now range, remember that is your y value. What is the lowest this graph goes? It does have a lowest point right here, the vertex. On the y line, that is a value of 0. How high does the graph go? Well, with our arrows, it goes up and up forever, so it goes up infinitely. So how did you do on domain and range? Is that starting to get a little bit easier as we move on?
Go Eagles.
Take a moment and set up the table and graph the next function and come back when you are ready to see how you did. So take a moment, absorb all this, and see how it compares with your work. When I was subbing in values for the table, you will notice I did not sub in any negative values for x. That is because we have not learned how to calculate a base to a negative power. If you are not sure what a number to the 0 power is, that anything to the 0 power is 1, that is okay. That is a concept we will learn later, so you may not have chosen the 0.01. The next number you sub in would be a 1, so 3 to the first power is just 3. Then you sub in a 2, 3 to the second power, 3 times 3 is 9. Sub in a 3, so then we have 3 to the third power, which would be 27, and then 3 to the fourth power, which is 81. When you go ahead and plot those points, they are not all going to fit on your graph, on your coordinate plane, but it's enough for you to get an idea that it is an exponential graph. It is approaching the asymptote at y equals 0. It will never go below that x-axis, which is the line y equals 0. So take a moment, make sure your table and your graph are accurate. The domain, remember, is your x values left to right. Well, it continues forever to the left, negative infinity, and it continues forever, because it's going slightly up and to the right, forever, so positive infinity. The range is interesting as far as how low it goes on the y-line. It is approaching 0, but it never quite hits it. So that's why we're going to do a soft parentheses right here in front of the 0. And then it goes on as far as how high it goes on forever to infinity. This is, in fact, an exponential graph. Now, what happens if instead of graphing, we just simply look at a table and make our prediction as far as what kind of function it is? Well, based on the 3 examples we did, you might be able to come up with these little shortcut rules. A graph will be linear if you are adding or subtracting the same number every time to get your new y values. It is a U-shaped quadratic parabola when the y values are changing in a pattern. And we saw that the y values went up and then they came back down. Exponential, which is the last one we just did, you are multiplying or dividing by the same number every time to get the next y value. When you are done writing down those 3 hints, go ahead and move on to the next slide. So let's look at our first table here. We want to look at the y values. Now remember, f of x is the same as y. So the question is, how am I getting from 16 to 64? From 64 to 256? The numbers are going up, so I'm going to predict it's multiplying or it's adding. Well, if I add, I'm not adding the same number to get from here than I am from here. I'm going to predict I'm multiplying. Well, I know 16 times 4 is 64. So the difference there is we're multiplying by 4. Now, to get from 64 to 256, is it multiplying by 4? Well, let's just take a moment and double check. 4 times 4 is 16. 24 plus 1 is 25. Yep, we are in fact multiplying by 4 every time. So what kind of function has us multiplying by the same number every time? The answer is it's an exponential function. So we can actually answer that question without ever having to graph it if we are given a table that is in fact exponential. So the little note you might want to remind yourself, this is happening because we are multiplying each y value by 4 to get the next one. Once you have the table written down, and you can just write the statement, you don't need to write A, B, and C, but I would like this because statement. This is crucial. If you can see that you are multiplying to get the next value, you can remember it's exponential. Here's our next table. What are we doing to get from 7 to 15? Well, there's no number if I count by 7s that will say 15, so I'm not multiplying, but I know I'm going up. It looks like we're adding 8. How do I get from 15 to 23? We're adding 8 again. But then to get from 23 to 15, we're not adding 8 again. We're actually subtracting 8. And then we're subtracting 8 again. This looks like it's following a pattern. We're adding 8, subtracting 8, subtracting 8. Do you remember which type of function shows a pattern? If you said quadratic, you are correct. Take a moment and write that statement, that this pattern generates a quadratic function. And then a little note you might want to write yourself that this is because we are adding or subtracting 8 each time. Once you have that down, move on to our final example for today's lesson. Here is our table. We are going from 9 to 14, which is add 5. From 14 to 9, we're adding 5 again. From 19 to 24, we're adding 5 again. It looks like every time we are adding 5. Which kind of function has you adding or subtracting the same amount every time? Hopefully you said linear at this point. That is in fact a linear function. You only need to write the sentence. You do not need to write down the A, B, and C. The reason it was linear is because we were adding 5 every time. So now you should be able to look at either a graph or a table and decide whether the function is linear, quadratic, or exponential, as well as give its domain and range.